All right, so this is the second part of going over the answers of exam number 2. We're starting with question 8 here. 25.0 milliliters of 0.50 molar lead nitrate is added to 4 separate beakers containing, okay, and then we're given different things, okay, some sodium chloride, some sodium hydroxide, some sodium phosphate, and some sodium acetate. After addition of the sodium nitrate solution, how many of the beakers will form a precipitate? And we're given answers 0 through 4, okay? So we're gonna use the solubility chart here to help us. And basically what we're gonna do is looking for, when we do the double displacement reactions, these are, anytime you see a solubility chart, it's a double displacement type reaction. Are we going to have anything that is insoluble? So we have sodium chloride in beaker 1 and lead nitrate. That means we can do, when we do the double displacement, we can have lead chloride forming and sodium nitrate. Well, all alkali metals are soluble. So sodium nitrate that could form is soluble. We know soluble means no precipitate, okay? What about the other option, lead chloride? Lead chloride, well, we go down to chloride. Chlorides are soluble, but lead is an exception, okay? So beaker number 1, yes, we have at least one precipitate. Sodium hydroxide, again, sodium nitrate, soluble, but lead hydroxide now we're looking for. So we go down to hydroxide salts. They're all insoluble except alkali metals, ammonium, strontium, barium, and calcium. We're not any of those, we're lead. So yes, lead hydroxide is going to make a precipitate. So beakers 1 and 2 will both form precipitates. Next one, sodium phosphate. Sodium nitrate again could form. We know that's soluble from this first rule. But we're looking for lead phosphate. So go down here, insoluble salts. Phosphates are insoluble except for alkali metals and ammonium. Lead isn't one of those. So beaker 3 is also going to have a precipitate. Last one is acetate, sodium acetate. Sodium nitrate, again, it's not going to be soluble, but is lead acetate insoluble? So we go down here and look at, soluble salts. Acetate soluble, and there's no exceptions. So that one's not going to make a precipitate. The first 3 are, and so our answer is going to be 3. During a summer research internship, you are asked to do some lab work to run on samples that will come in from the field. You need to prepare a 0.3 molar sodium hydroxide solution, but you only have 6 molar sodium hydroxide on the shelf. What volume of water must be added, okay, to 10 milliliters of 6 molar NOH to make a solution that is 0.3 molar sodium hydroxide? All right, so this is a dilution type question. So the dilution formula is M1 V1, okay, where M is molarity and V is volume, equals M2 V2, all right? You also could put initials and finals here. So what do we have? We have 6 molar. We actually we have 10 milliliters of 6 molar. So we have 6 molar here. 6 molar. And we have 10 milliliters as our initial volume. And we want to make a 0.3 molar solution. So it's going to be 0.3 molar times V2. And V2 is what we don't know. So that's 6 times 10, that's 60. So it's going to be essentially 60 divided by 0.3, and that will get us our answer, well, close to our answer in milliliters. What is this telling us? So that 60 divided by 0.3 is 200 milliliters. So that's telling us our final solution is going to be 200 milliliters of 0.3 molar sodium hydroxide. But to get to that, we're adding 10 milliliters. So we are going to need 190 milliliters, right? Because we already have the 10 that we added. The total volume is going to be 200. We're assuming the volumes are added. Okay, so the answer there is 190. Okay. Question 10. A cold spoon is placed in a hot cup of tea. Which of the following is true? The spoon and the tea will stay at the original temperatures? No, that would be magic if things could just always stay at the same temperature when hot and cold come together. The spoon will gain all the heat until the tea is cold and the spoon is hot. No, they're not going to be at the same temperatures or the inverted temperatures. The spoon will increase in temperature, but the tea will remain. No, they're both going to transfer heat, right? Heat is going to transfer from the hot object to the cold object. So it's going to be the last one. The spoon will gain heat and the tea will lose heat until the tea and spoon are at the same temperature. Most people got this one right. Somewhere in between the two values. Which of the following is the standard state of iodine? Okay, this is just testing your knowledge of what standard state means. Iodine is a solid element, and so it's I2. If you didn't know that it's a solid, no worries. You can also know that delta H of formation is 0. That's how delta H with the degree symbol is defined. It's defined as in the standard state. So just the fact that this said 0, it's basically asking you which one's 0. Okay. Or you could have known that iodine is solid and that's a diatomic element, which you should know because halogen, right? Okay. Why does breathing helium makes one's voice sound higher? Helium does not follow the ideal gas law. Heliums are less reactive. No, the reason is because they're moving faster, okay? And we mentioned in class when I did the demo that if I had inhaled sulfur hexafluoride, it's a really large molecule, which according to kinetic molecular theory would travel more slowly. My voice would sound like Darth Vader and be very low. Given the following data, calculate the delta H for the reaction using Hess's law, okay? All right, so people had some problems on this one. I'm gonna get some more whiteboard space here and show you what we start out with. I'm just gonna write down what we are asked for. We're asked for this one. We're asked for the delta H. Remember, Hess's law is basically we're trying to add up individual reactions to give a reaction that's an unknown. So we're trying to calculate the delta H for that. And we're given, okay, the things we can play with, the reactions we can move around and play with are Mn plus O2 goes to MnO2 and O2 plus H2 goes to H2O2. That delta H is given to us all in the same units of kilojoules per mole. And one last one, burning of oxygen, of hydrogen and oxygen gives water. And that has a certain change in enthalpy. So that's what's given to us in the problem. What we want to do in these problems is look at, what things do we want to flip, okay? And so manganese here is on the left. And in this reaction that's given to us, manganese is on the left. So that's good. I'm not going to want to flip that. Also, you'll notice, right, MnO2 is on the right and MnO2 is on the right. So I don't want to change that one. What about oxygen? Oxygen isn't in the equation here. Hydrogen isn't in it, but hydrogen peroxide is. And hydrogen's on the right here, and hydrogen's on the left here, and there's a 2. That is telling me that I'm going to probably have to flip this thing and multiply the whole thing by 2. So if I multiply the whole thing by 2, I'm going to put 2's in front of that, and I'm also going to have to times that by 2, right, the delta H. But now I'm also flipping it, and so that's going to get me 2H2O2 goes to 2O2 plus 2H2. And I'm flipping it, so that's going to make this whole thing negative. When you flip an equation, it makes an exothermic and endothermic, and an endothermic and exothermic. So 176 times 2, then flipping that to be positive, that's going to get me 375.2 kilojoules per mole. Okay, and then this one, oxygen, is not in the original equation. Hydrogen isn't, but water is on the right. And look, I have 2 waters and 2 waters. So that's looking to be nice. So basically what we're going to want to do is we're going to add, I'm just going to call this equation 1. We're not going to do that one because we modified it. Call this equation 2 and call this equation 3. So if we add all these equations together, 1, 2, and 3, what's going to happen? Well, I had manganese, and can manganese cancel with anything? No. Of these 1, 2, and 3, there's no manganese on the right. So I'm going to be left up with manganese. I have oxygen on the left here. 1 oxygen on the left. I have another oxygen on the left. That's 2 oxygens total. And I have 2 oxygens on the right. So 2 oxygens on the right with 2 oxygens on the left. Those are going to cancel out and go away. Next, I have manganese. So those are going to go away. Okay. What else is on the left here? I have this one we're not looking at. We flipped this. So we already dealt with that one. Just adding 1, 2, and 3. Hydrogen. Hydrogen, I have 2 on the left here, but I'm adding it with equation 3, which has 2 on the right. So those are going to go away. And the only thing I'm left with on the left here is in equation 3, the 2 H2Os, which lo and behold, that's what I want, right? Manganese dioxide, manganese oxide, manganese 4 oxide, I should call it, has nothing to cancel with, so that's going to be left over, and same with the 2 H2O in the last equation. So now I just have to add up this number, and this number to get my final answer. And that ends up being negative 716 0.1 kilojoules per mole. So that's my final answer. And so if I go back to our problem, that was one of the answers. Okay, we'll keep on going in the next video.